Okay, everyone. I hope everyone is doing well today. Again, my name is Heath, your host for this deeper dive webinar. Again, thank you all for being here. I couldn't be more excited to be talking with all of you today and sharing this new feature from Losant. So today we're going to be taking a deeper dive into a new edge offering from Losant, the Losant Embedded Edge Agent. Today we've got a couple different speakers with me. Again, my name is Heath. I'm joined today by Brandon Cannaday, our Chief Product Officer, and Anthony Canterbury, our lead backend engineer. Before I go any further, I do want to let you know that we are recording this webinar. And so that's so we can provide the replay available to you in a few different ways. After this webinar, we're going to send you an email with the link to the replay, and the recording will also be made available on Losant's YouTube page, as well as our deeper dive page on our website. Now, we love hearing your questions, so I would like to point out a few key features in the Zoom conference. You can use the Q&A feature or the chat feature to post questions, and I myself will be monitoring those throughout our time together. Then at the end, I'll moderate a Q&A session with Brandon and Anthony with those posted questions. Let's do a quick review of Losant and our enterprise IoT platform. Losant is an industry-leading IoT platform. As an application enablement platform, Losant provides enterprises with the building blocks they need to create their own IoT products. The Losant platform consists of 5 key components to help customers achieve that. First, end user experiences. End user experiences allow you to build a fully functional web interface that lets your users interact with your connected devices. Then we have a visual workflow engine. It's the low-code brains of your connected solution. It's how you trigger email notifications, create events, send commands to connected devices, and much more. Next, data visualization, which also allows integration with Jupyter notebooks, which allows you and your end users to see what your connected devices are up to. Then we have devices and data sources. This allows you to create a digital twin of your devices in the field, as well as integrate with other services that have the data you care about. And today we're going to talk about edge compute, which is a suite of functionality that enables you to execute business logic right at the edge. Our customers and partners utilize all 5 of these components to create the robust IoT products that they put in front of their end users. Losant is a leader in the industrial, telecommunications, and smart environment spaces, and we've offered this platform for all sorts of customers, ranging from startups to companies in the Fortune 100. If you're interested in learning more, please reach out, and we will be happy to set up some time for a much more in-depth conversation about how Losant can help you deliver a connected solution. Now, while Losant does provide the software foundation for IoT, we've surrounded ourselves with a great ecosystem of partners that help create this IoT solution. This includes strategic partners that we share go-to-market strategies with, solution partners who work with us and you to develop your end-to-end IoT solution, and technology partners that provide the hardware, connectivity, and other services to round out your IoT solution. Again, I couldn't be more excited to have you all here today. I'm going to pass this virtual mic to Brandon to get us started on this deeper dive. Again, as you have questions, please do not hesitate to ask them using that Q&A and chat feature, and I'll be sure to jot those down so we can get to that in our Q&A session. Brandon, over to you.
Thanks, Heath. Yep, once again, my name is Brandon Cannaday. I'm the Chief Product Officer here at Losant. I'm going to be walking through one of our newest offerings called the Embedded Edge Agent. It really augments our existing edge compute functionality in pretty exciting new ways. I'm going to cover 2 main areas here. I'm going to cover what it is and a lot of the use cases, and then I'm going to take a fairly technical deep dive into some of the code that is required. I know it's a low code offering, but there's a little bit of code that you're still responsible for when it comes to the Embedded Edge Agent. Let's first talk about what it is. The Embedded Edge Agent brings our low-code visual workflow engine. It's been there since day 1 and takes it to much smaller and resource-constrained devices, and devices so small that they may not even have an operating system, and that's what I'm going to show a little bit later. And this is quite a bit different than the Edge Agent you might be familiar with, the Gateway Edge Agent that runs on kind of those full Linux capable gateways with the Linux operating system, plenty of memory, plenty of hard drive space. And there were a lot of examples where customers they really wanted that low code environment, but on much smaller devices. So getting into the use cases, getting past what it is, and let's talk about why it exists. And I bucket the use cases into two kind of primary opportunities here. The first is for new product development. If you're a manufacturer or the creator of new devices or sensors or controllers, that's going to include new firmware, the EEA could be a really good fit, a good opportunity to include the runtime into the firmware, directly into the device, and it adds the speed and agility of a low-code environment into something that's traditionally quite hard to update. Requires code, requires OTA. And the other primary bucket of use cases is for off the shelf or existing gateways and controllers that may offer what's called programmable application space. And this is different from the gateways that run the full Gateway Edge Agent, in that those are just general purpose gateways you can run any software. There's a lot of gateways out there and controllers out there that do a specific or solve a specific problem, but they do offer a little bit of programmability. Usually you have very limited amount of memory and disk space to use, and the Gateway Edge Agent won't fit there. And they're programmable in a lot of different languages, from Java to Python. And so the EEA can fit and run in a lot of those environments, really add some low code ability to augment and extend some of these off the shelf gateways. So that's the two primary use cases that this fits. And I want to dig a little bit deeper into kind of that new product development. This is where I think the EEA really shines and can really add a lot of value based on what you might be creating. And the example I want to show here is an industrial controller. Every piece of equipment out there has a controller and it has firmware in it. So if you're out there, an organization about to create a new controller, it's a really good time to think about, well, what additional technology can I add to that controller's firmware to make it, more future-proof, provide the ability to extend and augment its functionality after it's delivered. And the main reason to do that is, when you ship a new device or controller, it's really rare that the firmware that you put on there solves all problems for the entire life of that controller. You will constantly get feedback from customers demanding, no, I'd like to do this. This slight tweak, what you've determined in your lab or testing environment may not be the same when the equipment gets out into the field. So you're likely to make revisions to that. And the EEA makes those changes very fast and simple to do, even for non-developers. And I've got a couple examples here of common changes that we would see after the equipment's been handed to a customer and out in the field for a while. The first one is certainly the changing telemetry data that's collected. In an IoT solution, we're seeing a lot of controllers starting to be revved to think about reporting telemetry data up into the cloud environment, or maybe to another gateway if it's inside a facility. And you don't often know exactly what telemetry data is required. So you kind of make a starting point based on the best information you have, and you may want to add some telemetry data. Maybe you're collecting too much and you find, well, we don't need to send these sensor readings because they don't have any value to the customer and they're just consuming bandwidth. The other one is updating control algorithms. The primary purpose of a controller is certainly to control the equipment. So it's taking sensor information, it's taking inputs, throttle, oxygen levels, whatever it might be, and it is running that through its control algorithms to then feedback and control the equipment. And especially with the rise of AI, we're seeing some complicated algorithms that get pushed to these devices, and you may not have these algorithms until you've got thousands of these in the field and you're collecting this data, and then you might find an algorithm that you want to apply back to that control. Maybe it's for safety or efficiency, and changing those in a traditional way, an OTA update, can be time consuming and difficult for your customers. And then the last is adding new capabilities. So we're seeing a trend of hardware vendors shifting to what's called software-defined functionality. Inside this controller, inside this equipment, is a lot of different data. There's a lot of functionality available, and you might discover, oh, there's a new feature we can ship without changing the hardware. It's just using the hardware in a different way, solves a unique and novel problem. Let's add that capability. Let's ship that out, and then the customers get new value with the same hardware. So this is just kind of one example to be thinking about. You know, it's always been possible to do these things, but what the EEA really does is make these changes much easier to do in that drag and drop visual way versus, you know, reapproaching your firmware developers, or a lot of times you've outsourced development to a firmware agency, pulling them back in and doing firmware changes. You really want to get that power into your hands and your operators' hands to make those changes. And, you know, this has been a strategy for ours for a long time. You know, our low code visual workflow engine is kind of the heart of Losant. It's the brains of every IoT solution built on Losant. And we've been constantly pushing, you know, down the stack, providing this environment for smaller and smaller devices in different use cases. So with this, we've kind of completed our technology stack of low code. Now we're going to constantly add new capability, new features, new nodes. You know, one of our core values as a product team is to continually push new features and new capability to our existing customer base and certainly new customers. So really with this release, we've got workflows starting at the embedded down to small devices. We've got the edge workflows for the gateway that we've had for many years. Then we switch into the cloud. We've got application workflows for alerting, notifications, perhaps protocol transformations. And then we've got the experience workflows. So that is the business logic that controls the actual customer interface. So when customers are interacting with these devices and data, they can trigger these experience workflows to handle those requests. So before I get into now how does it work, cover the what and the why a little bit, let's get into how. But how I want to do this is we'll start with a demo. And what I'm showing here is an ESP32, the Rover kit. This is a really nice development kit, really cost effective. The ESP32 is a really popular board. It's in a lot of production devices. It's a Wi-Fi and Bluetooth module. It's also great for kind of your proof of concept and development work when you're experimenting with, you know, what might be required in my device and my hardware. And they've got these nice kit sets around it. And this is a great example of a constrained device. These have no operating system. They are very small, very low power. The Rover kit has 4 megabytes of memory. We find that the EEA requires a couple megs of memory and less, you know, to make it safe kind of work in any kind of workflow you're working with. So let's check out, first, let's dive into Losant and kind of check out what this device looks like in the platform. If I go into the device itself, you'll see it looks like any other device. The device class is embedded. So as part of this release, there is a new device class marking this device as the ability to run embedded workflows. Beyond that, attributes and tags work just the same. I've got a few attributes here. I'll show the workflow in a minute, but what this workflow is doing is controlling and then reporting some GPIO. So showing how an embedded workflow works with those really low level peripherals, in this case, general purpose input output, that's available on these modules. And then the debug panel on the left over here, the right over here, you'll see some data coming in. We pause that, and you see it's reporting some state in the value of these GPIO inputs and outputs. You'll see it's warning with an invalid time, but that's just because I'm running a embedded device that has no concept of time. It really highlights the portability of these embedded workflows. If you've ever done kind of firmware development on something small, you'll know a lot of them don't have real-time clocks. They don't know what time it is. So we've made it, the cloud and everything support that capability. You just pass in time since it booted and it will work. Now the cloud here is kind of complaining about this. 0 is an invalid time, but that's okay. 0 is interpreted, is ignored by the cloud, and it will timestamp it by the platform for when that data point was received. So let's jump over to the workflow. I'm going to dive into this a lot deeper, but for now, what's happening is I've got a timer, and every 5 seconds, I'm controlling these GPIO, these 3 GPIOs. I'm just toggling them on and off, essentially by incrementing a storage value and then modding it by 2. So that's just going to give me a number between 0 and 1 over and over again. So let's open the debug window for this device, and we'll see some data coming in. My timer is for every 5 seconds, so we'll see there's a payload right there. And then I also have a live window of this thing going on. I can wave my hand in here. You can see I'm not cheating. But every 5 seconds, it's going to turn these 3 LEDs on by essentially writing a 1 to the GPIO or writing a 0 to the GPIO. So the first thing I want to show is, some of that agility. Every 5 seconds is a little bit slow. So the first thing I'm going to do is speed that up. Let's go back to the workflow, make a change. I'm just going to make one quick change to the timer, say, well, blink it every 2 seconds. Let's save, we'll deploy. If you are familiar with Losant's Edge Compute offering, if you've used the Gateway Edge Agent, all of this looks familiar. We made it work as close as we could between the 2 different runtimes, 2 different ages or agents. So you had that familiar interface. So I'm going to version it and I'm going to deploy it to my embedded device. Let's go ahead and hit deploy. Now this will take just a few seconds to deploy. And while this is deploying, let's dive back into some technicals, figure out what is happening behind the scenes. So when I click deploy there, what's happening is it's taking that workflow or all workflows targeting that device and compiling them to a WebAssembly module. So this makes Losant's Embedded Edge Agent one of the world's first, might be the world's first low-code WebAssembly development environment. And you might be thinking WebAssembly and saying, well, that's for the web. That makes no sense for a device. But whereas WebAssembly was originally targeted for the web, what it ended up being was a really nice, fast, and portable assembly environment. So you can compile WebAssembly and run it pretty much anywhere. And what I'm highlighting here is just a subset of runtimes. Here I've got 4 of them. I'm actually using Wasm 3 in my example. It's written in C. It works on a lot of embedded devices. These runtimes support a ton of different languages. So I mentioned at the very beginning, there is some code you're responsible for, and really the majority of it is implementing the runtime. You're responsible for the code required to get a runtime working. Then our workflows compile, or our platform compiles the workflows into a completely normal standard WebAssembly module, and then pushes that to your devices. And then that's executed by these runtimes. And there are runtimes supported in basically every language you might be comfortable with. And because of that, it's supported on basically any operating system, Windows, Linux. FreeRTOS and Zephyr aren't necessarily what you think of as traditional operating systems, but I'm using FreeRTOS in my example. And then you've got none. So you don't actually need an operating system at all to run several of these. If you've just got a control loop, a lot of these runtimes are completely portable C, and you can run it right on something like an ST chip. So coming back to the workflow, this has successfully deployed. And you can see you got a green check mark saying, we waited, it deployed. It takes maybe 15 seconds to compile and deploy. I can go ahead and click the live look again. It'll bring up the debug. You can see these are now coming in at every 2 seconds. So if I bring up the live window again, we can see the blinking is slightly faster at every 2 seconds. So that's a really simple way for, changing on the fly. I wanted my device to blink faster, but blinking LEDs aren't that useful. So let's make another change where we can control the LEDs from the cloud, and in this case, from a dashboard. So what I'm going to do there is go click Make Changes. I'm going to come back here into this workflow, and I'm going to replace the timer with a device command trigger. And you'll see the node palette is a little bit different on embedded workflows. You don't get every node that's supported by cloud and edge, but we've started with a really good set. And like I said earlier, we're going to be constantly adding new nodes. So let's go ahead and remove these top 3 nodes. And then we'll add the device command. So this node will trigger anytime a device command is received by the device. And we need to do a quick conditional because we want to make sure, we could be getting different devices or different commands, we want to make sure we, are checking for the right command. In this case, the command's name is set value. And just like before, the payload of the command will just be a 1 or a 0. So I'm sending the set value command with the payload set to 1 or 0. So I can directly connect it to the rest of the logic here, and it'll work just like it did before. So let's go ahead and save, deploy that. And we got another couple seconds to wait. And let's dive a little bit deeper into how this actually works. So what I'm going to reveal next after this works and I show the GPIO being controlled by command is like, how does the WebAssembly module talk to the GPIO? WebAssembly is completely portable. It doesn't really know what device it's running on. It doesn't know how to talk to the GPIO of your specific device. So what we've had to do is we've created what's called the EA API. And that defines a standard for WebAssembly imports and exports. And imports and exports are the way a WebAssembly module can communicate with your native code, with the code that implements the runtime. So that's the code that you're responsible for. You're responsible for implementing the runtime and then implementing all of the required imports and exports for the EA to talk to things like GPIO or accelerometers, or even the internet. So if you are using MQTT, your native code is what includes the MQTT client. And we do document the MQTT specification for, well, when you deploy a new workflow, this is the topic it's going to deploy to. And you can accept that WebAssembly module, publish directly via MQTT, and then push it into the runtime. So these imports and exports are what are used to communicate with the device itself. So in order to send the command, we have a device input block that can send commands to devices. So if I go in here, if you're not familiar with the input control block, it allows you to add any number of controls. And with those controls, you can add some buttons. And a button is what will take action when that control is clicked. So in this case, I've got the toggle, which lets me turn the GPIO on and off. When that is clicked, or when the submit button is clicked, it sends a command to the EEA device called set value. And here's a nice little pro tip. The payload that you send does support templates. So in this case, value up here, the variable value is going to be a Boolean, true or false, but my device is expecting a 1 or a 0. So I can use a little template here, say if value, send 1 as the payload, else turn 0 as the payload. So this is the block that's sending that command. And that lets me invoke these commands to turn these LEDs on and off. So let's get into a little bit of the GPIO here itself, or the ability to invoke functions defined in native code. What I've got here is what's called a registered function node. The registered function node allows workflows to invoke functions defined in your native code. And this is the primary way, a very important way, and a very important concept to understand for working with the embedded edge agent. So in this case, I am invoking a function named GPIO set level, and I'm passing it 2 parameters. I'm passing it the index of the GPIO I would like to set, and then I'm passing the value, in this case, from data.payload, a 1 or a 0. So let's look a little bit at the code that's required to do that, the registered function GPIO. All of these are defined in the Embedded Edge Agent API. From a developer's perspective, when you are sitting down to write that firmware, this is a very important, this is a critical document. It defines all of the built-in or default imports and exports, all the stuff the engine requires, and then all of the stuff that's custom, which this is the registered function API. So this is my specific WebAssembly runtime. I'm using WASM 3. How you register functions, or basically import functions into a WebAssembly module, will be different based on whatever module you're using, but they're all very similar. So in this case, when I want to invoke GPIO set level, what's actually going to happen is it's going to look for an import named EEAFN GPIO set level. We added the prefix on here just to keep things safe. So if you happen to import a function that conflicts with other functions that might be imported, we added this prefix. So you don't have to put the prefix on here, the EAFN prefix, but when you turn around and register that function or import that function in code, you'll add that, that prefix to it. And what this function is doing is directly wrapping underlying capability. This is a really important concept to think about when you're defining or designing your registered functions. I could have created a function that says, you know, GPIO set level for input 18. And that function can only do one thing. It can only set the level for input 18. What I did instead was created a function that takes the two inputs, takes the pin to set, and then takes the level, the value to set that pin to. And what it does, it just invokes the underlying API call. So if I switch to that, here I am in the ESP documentation. So if I want to change the GPIO for something on an ESP, this is the function I call. This is the driver that they provide. And it, just like what I'm doing, it takes a GPIO pin number, and it also takes the level. So by registering one function, I am able now to completely control all GPIO from the workflow. So this is a really convenient way to think about how do I design my registered functions. Really, these are providing that middleware, that kind of driver system to expose underlying native functionality into the workflow. Very important functions to think about. Then if we switch here to a little bit more difficult registered function. Now, this is a different workflow. This is reading accelerometer data. And yes, embedded edge devices can run multiple workflows. In this case, I'm running two. And in this example, I am asking for 1024 signed integers. And you can see it over here in debug panel. I'm getting 1024 integers. And the reason I'm doing this is because I'm doing vibration analysis. I could do, you know, like a loop. I could add a loop, and then under each loop, I could invoke a registered function to read just one accelerometer reading. But I need fairly real-time control over this because vibration analysis requires a fairly consistent time between readings. So I want to send that command basically into the native code where I have real-time control over reading that high frequency data. I need these data points at roughly 1 millisecond apart. So I can, you know, subsequently pass this into FFT and get an accurate analysis. If you want to do FFT stuff or want to learn more about that, I want to draw your attention to this how-to guide. So how-to guides, you'll find them over here in their documentation. And this is currently the bottom one in the list. You'll find it there. This goes through how to use the embedded agent to do the FFT analysis. This runs on a Raspberry Pi and uses a Python WebAssembly runtime. So if you're kind of new to this, you may not want to step directly into the embedded code. That can be a little much. So this is a nice walkthrough or a guide for doing this on a Raspberry Pi with Python. So let's talk a little bit about what's going on behind the scenes. One of the challenges with WebAssembly and that interface to communicate between WebAssembly and your native code is that it only supports a few data types. So if I come back here, let's scroll up to this diagram. Sending data into WebAssembly or exporting data from WebAssembly, if you look at the WebAssembly spec, you get numerical types. That's it. Some integers, some floating point numbers. That's it. I'm asking for an array of numbers. That's not any of those. So what has to happen is we have to switch to pointers. So the WebAssembly has to allocate a chunk of memory and give it to the native code and says, well, here's a chunk of memory big enough to hold the array of numbers that you would like to give me. Please fill this buffer of data and then give it back. So if I go in a little bit down into again, the Embedded Edge Agent API document, scroll down to the registered functions output. Let me click on this output here just to remind everyone I've got one output. This has no inputs. I'm not sending any information into the native code. I'm just requesting the native code to output information. What I'm asking for is a signed integer array of no bigger than 1024 items. And I'm going to, when that comes back, I'm going to put it on the workflow at vibration. So you can see all those data points here. So if we go to the spec, this is really helpful kind of understanding how outputs, complex outputs map to a registered function. Come down here and click outputs. Draw your attention to what happens if you do a string or array or JSON. JSON and string are very similar. You might think a string is a pretty simple type, but a string is really just a buffer of characters. It's treated just like an array of numbers. It's a complex data type. So when you want to output one of these values, what's going to happen is your code is going to be given 3 arguments from the EEA. It's going to be given that pre-allocated buffer. So the EEA, what it's going to do, it's going to look again at your input and say, well, I need enough space to hold 1024 integers, and integers are 4 bytes. So you get 4096 bytes worth of buffer. So it's going to allocate that. It's going to be empty, and it's going to give you a pointer to it and say, here, please fill this buffer. And then it's going to give you the length of that buffer. Either in, if it's string, you'll get it in bytes. If it's an array, it'll just give you the length in elements. Basically, how many numbers can this hold? And this is for bounds checking in your native code. It's really important to do bounds checking everywhere. This is pretty low level stuff. When you're talking about raw buffers, your native code needs to check, well, how big was the buffer I just got, to make sure it doesn't do what's called a buffer overflow and accidentally write too much data. Because your workflow may say, well, I expected 512 elements. It invoked the registered function, but there might be a mismatch. The registered function may attempt to put 1024 elements in there and then start overriding some probably really important memory, and will cause usually some really interesting and hard to debug crashes of the application. So you get the pre-allocated buffer, you get how big that buffer is, and then it provides you another pointer, a small pointer, just enough to hold an unsigned 32-bit number. So again, 4 bytes. And you need to fill that buffer with one number, and that is the number of elements you wrote. Because even though you told the EEA, I want a buffer big enough to hold 1024 elements, you're not required to fill it. On arrays, it's probably likely you'll fill the whole thing, but on strings, strings are often dynamic. You don't really know what the length of the string is going to be every single time. So what you'll put in that field is the largest possible string. So if you're invoking a register function, it can return a string between 10 characters or 10 bytes and 200 bytes. You'll put 200 bytes in there. Guarantees your buffer is always big enough to hold every type of string that you'll receive. And then what you send back is how much you actually wrote to that. That allows the EEA then to parse that string appropriately, add it to the workflow appropriately. So let's check how that looks in code. So this is what's happening. This 32-bit array, these are the outputs that I just showed earlier. That expands into these 3 input arguments. I get the buffer to fill, I get the length of that buffer, and then I get another pointer that I'm supposed to write how much data I write to that buffer. So here I'm actually reading the vibration data. So looping 1024. Vibration data is usually one axis on an accelerometer, in this case, just the x-axis. And then I am copying that to the readings array. So reading, copying it, and then I'm delaying 1 millisecond. So this is where the native code gets a little more real-time control over how far apart those readings are. And then when I'm finally done, here is where I'm copying that 1024, the number of elements I wrote to that buffer here. So you'll see a lot of cases in the EEA API and register functions where pointers are involved. So I really wanted to spend a moment on that to talk about why that is. And just to reiterate that one more time, it's because this interface between the native code and the WebAssembly module is really restricted on what types of data it can directly send. So as soon as we get to complex stuff like strings and arrays, the EEA inside the WebAssembly module takes care of allocating the memory and then passes a pointer to that memory out to your native code to fill and populate. A quick pro tip here, you might see this debug output looks a little different than you've seen. It's only got one property. If I click the debug node, I specified that property here. Now, when it comes to cloud and the Gateway Edge Agent, this isn't that critical. When it comes to embedded, this is very critical to think about. Embedded environments are very memory constrained. And when you hit a debug node, it is creating a JSON, a string representation of the workflow, and it's invoking a native function through the EEA API. Actually show that. It's called send message. So this is another area to really emphasize how sandbox and isolated a WebAssembly module is. It doesn't know how to talk to the internet. It doesn't know how to talk MQTT. It can't talk to system resources. It has no external dependencies. So whenever the EEA or when your workflow wants to send a message to Losant, it invokes this imported function called send message. And here it passes some pointers. It sends a pointer to the topic, how many bytes the topic is, and the whole payload. So if your workflow is growing and you call send message, you can all of a sudden consume a lot of information. You know, that's 1,024 integers, all serialized to JSON. You know, in my testing, it was around 5 or 6K. And when you get into these resource constrained devices, you got to be really conscious of how much data are you trying to send to Losant. Very easy to run out of memory there. So what happens is when you specify these properties down here is that's actually compiled and sent to the edge agent. So it will only send up this property. So you can be, you can control the amount of data you're trying to send up through a debug node. The other area I'll point your attention to is the walkthrough. It's a great piece of content. I've talked a lot about the memory model. The walkthrough has a whole chapter on that. It really goes into a little more detail of really how that memory works, how data is passed back and forth between Losant and the WebAssembly module and your native code. Okay. Next thing I want to touch on is the differences between the GEA and the EEA. A lot of you on the call might be familiar with the Gateway Edge Agent. This is what's run as a Docker container on really any gateway. But there are a number of differences between the two. The first and foremost definitely is how, you know, just what it is, how it's even distributed. The Gateway Edge Agent is distributed as a standalone service. It's installed as a Docker container. So think of it like any application you install on any computer, you just install it, run it, and it's good to go. The embedded edge agent, on the other hand, is designed to be embedded, included into another application or firmware. It's not installed separately. It's not a separate service. It's written right into your edge application or your firmware. That's kind of gets back to, you know, the code you're responsible for is implementing that WebAssembly module, implementing the MQTT client. What's nice though is, you know, once the hard work is done, you know, getting that WebAssembly module implemented, then you switch over to low code world where people from operations can kind of go in there and change behavior without that difficult firmware. In terms of dependencies, the Gateway Edge Agent, you know, we prefer Linux, but it requires an operating system. It requires something that can run Docker. The Embedded Edge Agent has no external dependencies outside of a WebAssembly module or WebAssembly runtime. And then that EEA API is the interface that controls how the Embedded Edge Agent does talk to things like system resources and the internet. Kind of an interesting technical note is on the GEA, workflows are interpreted. So if you've ever exported a workflow and looked at it, you can export workflows on the top right corner of the workflow editor. You'll see a JSON representation of a workflow. That's pretty much exactly what's sent to the Gateway Edge Agent. That JSON doesn't know how to interpret something like a math node. It includes the expression, whatever you type in a math node, that'll be in that JSON, but it has no idea how to evaluate that. So the Gateway Edge Agent, all of the code that makes that up, knows how to interpret and evaluate those workflows. The Embedded Edge Agent, on the other time, is compiled, completely self-contained. So there's not a separate service running somewhere accepting the expression you typed in a math node to evaluate it separately. That's compiled directly as WebAssembly into the module. And what's nice about that, it keeps these workflows quite small. The workflows I've done with pretty full vibration analysis, they end up at 130, 150K kilobytes in size. And that's because we've done a lot of work optimizing those workflow sides. The Gateway Edge Agent has all these built-in connectors, all the nodes, all the logic to implement every possible node is always in the Edge Agent. It makes it pretty big. If you don't use a node in the embedded Edge Agent, it's not compiled into the workflow. Saves a lot of space. And what I was saying on that, the Gateway Edge Agent does have a lot of built-in industrial connectors. It's sitting on an operating system. It's sitting on Docker. It knows how to talk TCP IP. It can talk MQTT. So all that stuff's built in. The embedded Edge Agent requires you as a former development or developer to implement those connectors as registered functions. And the biggest thing is the required resources. The Gateway Edge Agent requires about 1 gigabyte of storage. It's the image size. We do have Alpine versions that get that a lot smaller, a couple hundred meg. That's because there's an entire Linux user land compiled or in that Docker container. So those containers are pretty big. And it requires about 512 megs of memory. Something like a Raspberry Pi 2 and up is kind of what we say. The embedded Edge Agent, on the other hand, is much smaller. If you want to persist your workflows, it's about 256K of storage. Workflows, there's an option if you go through the the MQTT specification, you can actually you can tell Losant to zip a workflow beforehand, but if you don't do that, workflows won't be any bigger than 256K. So you don't need a bunch of storage to persist it. In my example, I'm not persisting a workflow. Every time the device comes online, it sends what we call the hello message to the cloud, says, I don't have any workflow, and the cloud will turn around, compile, and publish the workflow. So persisting workflows isn't required. And what we've seen is, I think 2 megabytes of memory is very comfortable. I've never seen anything require more than that. On my example with ESP, I'm running about 512K, or about a little less than a meg, but 2 megs is really that comfort area. That's because, your workflows are going to be, 256K at most. You'll need probably 2 copies of that. You'll have one running. You'll need to bring another one in over MQTT. So that's about half a meg already. You bring in the runtime and MQTT, you're going to be up about a meg. Before I move on to my last slide, I do want to hit a pro tip. Developing that WebAssembly runtime, I'm not going to sugarcoat it. That'll be the most challenging part. Creating the code, creating the firmware to get the WebAssembly module working for the very first time. We do have a really nice walkthrough that I would recommend. This kind of gets you acquainted with WebAssembly. We do create a WebAssembly module called the Hello World module that kind of strips out most of the API just to get it down to the core of getting WebAssembly to work. Now, when you start switching over and after you get WebAssembly working at all and you start building workflows and deploying them, what you can do instead of having to get all of MQTT working and receive these workflows over MQTT, when you have an embedded device up in the device actions menu, you'll see this option here called request WASM. WASM, WSAM is short for WebAssembly. You click that and you can just request one of these WebAssembly modules. So you can request the module that would be sent to this device and you can kind of load it directly from disk or whatever. This is excellent for debugging. I can't recommend it enough. Couple options here, pretty technical. Stack size, you can mostly leave that at 32K unless you've got some really out there workflows. You can control the trace level for development. Definitely change that to verbose. There is a function, a very important function in the EEA API called trace. It's an imported function that the EEA will invoke to send debugging information whenever it's making decisions, executing workflows. It's just sending a nice little message. So you'll definitely want to, oh man, can't find that. There we go. So definitely want to know that this pop-up exists when you're in initial development. This is going to be really helpful for you. All right. Lastly, I have talked a lot about these resources. This is a deeply technical concept. So you'll really want to look through these resources right here. You'll find them all in our documentation, but you got the walkthrough, great place to start. You've got that guide that uses the Raspberry Pi and Python to do some vibration analysis. We do have built-in fast Fourier transforms and RMS to handle vibration analysis use cases. For the firmware development, kind of that hard part of using the embedded edge agent, the API is critical. And then when you want to receive workflows over MQTT, we do also document the MQTT specification. So with that, I will hand it back to Heath for Q&A and wrap up. Heath?
Yeah, awesome, Brandon. Thank you so much for that that great overview of the new EEA and kind of a great walkthrough of how to get started with it. First things first, before we get to our Q&A, I just wanted to say that, as always, no feature here at Losant is released without being fully documented. As Brandon showed you quite a few times, we are fully documented for our EEA. So you can head over to docs.losant.com to get started there. Brandon gave you some additional resources as well. We've also got our forums, forums.losant.com. So when you get started with this EEA, you can start to ask questions about the Losant side of things there. We also have some tutorials in our blog, as well as the replays that I mentioned at the very beginning of this, of this deeper dive series on our website at losant.com/deeper dive webinar series. Okay, I see we have a few questions. The first one that we want to get started with is actually, Brandon, probably for you. At the beginning of your demo, you started to show the frequency of those blinks with the GPIO, or the GPIO, excuse me. So when you're switching from 5 seconds to maybe a half-second blink, does that directly affect the battery life long-term?
It can. So obviously keeping a light on will impact battery life. When it comes to the workflow itself, it's constantly being, or the EEA itself, there's really very little impact of a timer and executing workflows. How it works behind the scenes is you can find this in the API. There's a function called EEA loop. And this goes back to kind of the embedded world. The WebAssembly, they're working on it, but they don't have a concept of threads. So the WebAssembly module can't run itself. It has to be hosted in a thread outside, or I was doing a FreeRTOS task. So you have to constantly pump the EEA with loop. I'm doing it about every 100 milliseconds. So whether it's triggering timers or not triggering timers has very little impact on the overall battery life, but certainly leaving a GPIO on, powering an LED for longer. Although 2 seconds versus 5 seconds back and forth, I don't know, to do some math on how long a light would be on over the course of an hour. But so just making a timer, I guess short answer, making a timer faster won't have much impact on battery life unless that timer is doing something that does consume a bunch of battery. Well, I guess in this case, it is sending a lot more data over the debug node. So yeah, it could, it absolutely could, but it really depends on what the workflow is doing with that timer.
Perfect, thank you. And actually now, Anthony, a question for you. Brandon mentioned a couple times the workflow being compiled and WebAssembly being involved. Could you talk a little bit more about how we go from like a cloud workflow to it being compiled and then sent down to device?
Yeah. Hi guys. So for the compilation on this, like you said, we've got the workflows in that JSON format. So each time that you go to deploy it to the embedded edge agent, it takes those configurations that you've put in for your nodes and the workflows, and it takes all of the workflows that you're deploying presently to the device, and it converts that to Rust instructions. And the Rust instructions are then wrapped up in that API library that's also written in Rust. And it's all optimized for the embedded environment. And it's selective on what code it puts in there. So it's as efficient as we could get it, and we're continually tweaking it as we go. But then from that Rust instruction, then we compile it down to an optimized WASM bundle, which is then what is sent down to the device.
Awesome, thank you so much. Brandon, a question for you. Farhang asks, a typical microprocessor doesn't have 2 megabytes of memory. For example, Nordic Semi's very popular Bluetooth low energy chips have around 256K of RAM, but the EEA requires about 2 megabytes. They're wondering if we've done a survey or maybe have worked with somebody on low power processors that can actually run the EEA.
Yeah, that's a really good question. Yeah, the memory requirements does exclude, quite a wide family of those pretty small ones. There are a ton of boards in that 256K area. And, the reality was there was no kind of assembly language general purpose runtime we were able to create to get it that small. By the time you bring in the TCP/IP stack and TLS stack, that 256K turns into a very small amount of usable space. And really, it's enough to kind of fit a very domain-specific application. So those really small ones, yeah, you're probably still going to write those with code, piggybacking on kind of traditional OTA mechanisms to get those binaries updated. And you have to come up the stack a little bit when it comes to getting something like more of a general purpose runtime available in those. There are quite a few vendors that get that large. ST does have some family of devices with a couple megs of memory. But yeah, you are absolutely right. This is not a fit for those very small ones, those, the Bluetooth modules, like you said, or, there's a lot of popular cellular modules that have application space, but again, they're pretty small, pretty limited. So it's going to have to be a little bit bigger. It does narrow the field a little bit on which embedded devices can support. I think, we've done that research internally. I think that's a great task for us, is to add that to our documentation, kind of advertising. Here are some modules that we found out in the world that have enough space and are comfortably run the EEA. So we'll take that as an action item to do ourselves. But yeah, you highlighted a really good point.
Great, thank you so much. Just one question kind of before we wrap it up here. Brandon, you mentioned, fast Fourier transforms and RMS as released for this, this MVP, this first release. What other things are we working on for first class support with the EEA? Are you able to speak a bit on the upcoming roadmap?
Yeah, so release, we targeted vibration analysis. It's a use case we see quite often. Small smart sensors, there's a lot of those being developed now to take in vibration data and FFT it right on the device and send up the analysis. The next use case we're going to tackle is geolocation. So in the next release, the goal is we'll have some, geofence nodes, some ability to understand and provide some value for geolocation data. Because that's another big use case we see. We do have a number of partners in that area where, you can take a GPS or connectivity module, pair it with a daughter board that has, enough memory, and then execute, some real-time logic right in device for, did I come into a geofence or leave a geofence and do something interesting based on that. So we'll see some geofence stuff. We'll also see base64 encode nodes. Those are really useful for blob data. So a while ago, Losant released what's called blobs, which basically allow you to report arbitrary data, primarily for image data. So if you do have an embedded environment that does handle images, you'll be able to run the EEA, do whatever image analysis you need, base64, encode the image and report that directly to the cloud. So we'll have some more powerful encoding coming very soon.
Awesome. Thank you so much. So with that, everyone, we're going to go ahead and wrap this up. Again, if you have any questions or want to reach out for a more in-depth demo of the Losant platform, please reach out at hello@losant.com. And if you have any questions while you start to get working with this EEA, feel free to reach out on the forums at forums.losant.com. Again, thank you all for being here. We will catch you in the next one. Thanks so much.